Hello, this is iMathit with Samuel Oke. This channel is dedicated to helping young mathematicians reach their full potential as soon as possible. And in this lesson, we'll be looking into separable ODE. Well, separable ODE is not the only type of differential equation. We also have homogeneous differential equation. We have a exact differential equation. We have Bernoulli equation and lots more. So, well, probably separable ODE is the very first type of ordinary differential equation you will be exposed to. So that is why I have selected this simple problem to study for the study today. So the very first differential equation we have here is y prime equals 1 plus y raised to power 2. We can rewrite this as the y dx and equals 1 plus y raised to power 2. What we intend to do when solving separable ODE is we want to get all the components of the differential equation on the appropriate side so that we can integrate and then obtain the general solution for the differential equation. So we multiply both sides by ds, and so we have this, right? Now you will notice that we have the y component on the side of the x, right? So we want it on the side of y so that when we are integrating, the terms would be reasonable, right? And we'll be able to integrate easily. So, and to do that, you notice in this case, we would need to multiply both sides by 1 all over 1 plus y raised to power 2, right? And when we do that, we have 1 all over 1 plus y raised to power 2 dy, right? And that's going to be equal to, you notice that we cancel out that. So we have 1 there. Well, you can write it, and you can choose not to write it. So we have 1 ds, right? You can write that 1 or choose not to. So at this point, we are done with the separation of the variable. So we simply go on and integrate both sides. And that is the method. We separate the variable and then we integrate. So we have the integral of 1 all over 1 plus y squared, the y, and integral of 1 ds. So what is the integral of the left-hand side? So you probably know is inverse tangent of y, right? Arctan y. And the integral of 1, the x is x, right? And don't forget c, which is the constant of integration. So we need to get y all by itself so that we clean things up a bit. So we have y is equal to tan x plus c, right? Remember to put x plus c in brackets because it concerns everything there. And that is the general solution for that differential equation. Okay, now let's see the next one. These first two are quite very simple and straightforward. So in the second one here, we have y prime equals s raised to power 2 and multiplied by 1 plus y raised to power 2. 1 plus y raised to power 2 in bracket. So, and that's going to be the s equals x into bracket 1 plus y raised to power 2. Mind you, y prime equals the y, the s, right? It's the same thing. It's just different representation. So let's go on and multiply both sides by the s so that we can separate those components first. So we have the y equals s raised to power 2 and multiplied by 1 plus y raised to power 2 and multiplied by the x. So now we need to get 1 plus y raised to power 2 on the other side. You can see that, right? And that is where the separation of variable takes place. Now, how do we do that? So how do we manipulate that? You will notice if we multiply both sides by 1 all over 1 plus y raised to power 2, it will get rid of 1 plus y raised to power 2 on the right-hand side. So let's do that. So we have 1 plus y raised to power 2 dy equals, that will cancel out that, right? So we have s raised to power 2 dx. So at this point, we can integrate. And that is the method. I hope you get it. So it is just as simple as that. What's the integral of 1 all over 1 plus y raised to power 2? And that will be inverse tangent of y, right? So just like the very first one we did. So, and the integral of s raised to power 2 is s raised to power 2 plus 1 all over 2 plus 1. That will be s raised to power 3 and all over 3. Don't forget the constant of integration. It is essential when we are dealing with differential equation. When you are doing regular integral and you forget the constant of integration, it can be forgiven. But I don't think it can be forgiven here. So, and When we clean things up, we have y is equal to tangent of x raised to power 3 all over 3 and plus 6. This is the general solution for this differential equation. So mind you, you may be required to find specific solution, and that is known as initial value problem. In that case, you will be given some initial values that will help you to determine the value of c that you will put back into this equation to obtain specific solution. So now let's see the third one. This one is slightly more interesting. Well, if you are getting value from this lesson, remember to hit the thumbs up, and please subscribe to this channel for more educational content like this. So we have y multiplied by y prime and plus x, y squared equals x. So when we rewrite that, we have y multiplied by the x and plus x multiplied by y squared equals x. So I am bringing x raised to power 2, xy raised to power 2 to the other side. So we have y divided x equals x and minus xy raised to power 2. So you notice at this point we have something we can factor that side, right? So when you are factoring at this point, the tip I have here is make sure you factor negative of that y, so that you don't run into some problem when you are integrating. So let's multiply both sides by dx. So we have y dy equals so let us factor negative x out of that, okay? So we have negative x into bracket, so that will make y squared positive, right? And 1 negative, right? To factor it completely. So and multiply by ds. So the reason for that is so that you don't run into a problem when you have to integrate. So next is time we separate the variable. You can see. So at this point, to separate the variable, you will notice that if we multiply both sides by 1 all over y raised to power 2 minus 1, it will separate the variables, right? So that you get rid of y raised to power 2 minus 1 on this side. And so you have y all over y raised to power 2 minus 1 dy equals negative x dx, because y raised to power 2 minus 1 would have been cancelled on the other side. So it's time we integrate. So we have the integral of 1 all over y raised to power 2 minus 1 dy equals the integral of negative x dx. This is going to be a use substitution type of problem. Sorry, you notice I've been writing one day. I'm supposed to write y. You can notice from up there we have y dy. So I'm sorry about that. So the integral we have here is a use substitution type. Well, you can see a lesson on that on this channel, so you can go look into that. Well, let's go on and do that right now. I could put the link to that lesson in the description for you. You might need that. So you say let u equals y raised to power 2, such that what is the expression for the u dy? It's going to be 2y, right? So we cross multiply, or we multiply both sides by the y, right? So that we have 2y dy is equal to the u, right? That will be equal to the u. Good. So at this point, divide both sides by 2y, and you have the y equals the u all over 2y. So now, where we see the y, we put the u all over 2y. And where we see y raised to power 2, we put u. So that's the essence of that technique there, right? So we now have y all over, so u minus 1, instead of y raised to power 2 minus 1, and multiplied by, instead of writing the y, so we write the u and all over 2y, right? All of this is equal to, let us extract the constant of that integral. So we have negative 1, right? And integral of x dx. So, you notice here that this y cancel out this y, right? So what we have left there is integral of u minus 1 equal to, u minus 1 all over u minus 1 and multiply by the u and all over 2, right? So and this is equal to negative, what's the integral of x? That is going to be x raised to power 1 plus 1, right? Which is 2 and all over 2. And plus c, which is the constant of integration. Do not forget the constant of integration when you are dealing with differential equation. It can be forgiven when you are doing just ordinary integration, integral, when you are just evaluating integral. So we extract a constant here, which is 1 all over 2, and the integral of 1 all over u minus 1 is ln of absolute value of u minus 1. So, and that's equal to negative x raised to power 2 all over 2 and plus c. So I think we should multiply both sides by 2 to get rid of those 2 all over the place, right, on both sides. So the 2 cancel out that 2. So we have ln of absolute value of u minus 1 equals, so we have x raised to power 2, right? The 2 is gone, and plus 2c, right? So I shouldn't write 2c. It's just c. 2c is c, right? It's still a constant. So at this point, it's time we start cleaning things up a bit, right? So let us take the exponent of both sides so that we can get rid of the natural logarithm we have on the left hand side. So we are left with u minus 1 equals exponential e raised to power negative x raised to power 2 and plus c. So but instead of writing plus c, so I'm going to multiply that by e raised to power c. You probably recall that from indices, when you have addition of power of an exponent, so you can rewrite this as a product of the separate exponent, right? So that is why you have e raised to power c, then multiply by e raised to power c. Great. So where e raised to power c is also a constant, so I'm going to write e raised to power c as c in the next line. So and u is equal to y raised to power 2. So it's time we bring that back in. So we have y raised to power 2 minus 1 is equal to c e raised to power x raised to power 2. Right? So to clean things up a bit some more, so we have y raised to power 2, we add 1 to both sides. So we have c e raised to power negative x raised to power 2 and plus 1. So to get y by itself, we square root both sides, and we have y is equal to the square root of c e raised to power negative x raised to power 2 and plus 1. And there you have it. That's the general solution for that differential equation. So like I said, you may be required to obtain a specific solution, and that will be an initial value problem where they will give you certain initial value to work with. Please, if you are getting value from this lesson, give the video a thumbs up. Okay, let's go on to the last one. Well, you can pause the video and try this by yourself, because I think by now you probably have grabbed the idea. So pause the video and try this. Well, let's go on and do it. So we would have the y, the x would be equal to sin x and plus, when we bring y sin x to the other side, it becomes negative, right? So let us factor sin x from there, and like I told you earlier, try to factor the negative of the y component there, so that you don't run into some trouble when you are dealing with when you are evaluating integral. So that is why we would have the y dx equal, we factor negative sin x. So when we do that, so the y we have there is going to be positive, right? So and the 1 we need to multiply it by negative sin x will be negative, so that we obtain a positive value. So at this point, we multiply both sides by the x, right? So that we can so that we can perform the separation, right? So we have the y equals negative sin x and multiplied by y minus 1 and multiplied by the x. Okay. So next we need to get rid of this y minus 1 on the right hand side. And to do that, to separate the variable, so we multiply both sides by 1 all over y minus 1. So how do we do that? So when we do that, we have 1 all over y minus 1 dy equals negative sin x, and multiply by the x, because that y minus 1 down there will cancel out the y minus 1 we have up there. So it's time we integrate, because now we have separated the variables. So we have the integral. We are to evaluate the integral of y minus 1 dy, and it's equal to integral of negative sin x dx. So what is the integral of negative of 1 all over y minus 1? That would be ln of y minus 1, right? Absolute value of y minus 1. So let us extract the constant there. So we have negative, and the integral of sin x is negative cos x. So I'm putting negative cos x here, and I will not forget the constant of integration plus c. So next, we are trying to clean things up a bit now. So we have ln of y minus 1 equals minus times minus is plus, right? So we have plus cos x and plus c. So next, we to get rid of the natural log on the left hand side, we take the exponent of both sides, right? So when we do that, so we would be left with y minus 1 on the left hand side. So we have y minus 1, and that will be equal to exponent e raised to power cos x and plus c. And like we used to do, remember, we have to rewrite this. That should be c. So like we used to do, we have to rewrite this in a more easier form. So we have y equals exponential e raised to power cos x and multiplied by e raised to power c, and where e raised to power c is c, right? And plus 1. So we have y equals c e raised to power cos x and plus 1. And that is the general solution for that differential equation as well. So there you have it. And this is how to solve separable ODE. So in the subsequent lesson, we will be looking into how to solve homogeneous differential equation. So then we'll go on into exact differential equations. So come back for those as well. So and please remember to give the video a thumbs up and subscribe. Well, until next time, keep mathing it and keep winning.